Hello, welcome back. Algebra 1, lesson 4.7. That means unit 4, page 7 is what we are on. And today we're going to continue looking at exponential functions. Specifically, we want to see, well, what information can we gather from it when we look at it as a graph instead of an equation? So we're going to start by looking here. We've got a graph. The first key thing you should be able to identify is the domain. Remember, the domain is all of the possible inputs. So what are all the possibilities of things that can go into where the X is? And so when we look at this graph here, there's no restrictions horizontally because X is the horizontal value to the left or to the right. So there's no restrictions on it. So our domain is going to be from infinity on in the negative to infinity in the positive, which means all real numbers, right? So this has a domain of all real numbers. Let's see what this says. The set of all possible values input for X, okay, the input or independent value. For all exponential functions, the domain, that's key right there. For all exponential functions, all. What does all mean? All means all. Every single exponential functions, you already have the answer to this. It doesn't matter. You don't even need to look at the graph. You don't need to look at the equation. For every single exponential function, it will be a domain of all real numbers. Now, how do we write that? To represent all real numbers, we say, and then it says it's supposed to have interval notation for us there. Well, all real numbers can be expressed in interval notation as we're going to have a parentheses here. Remember, a bracket means it's going to be included, but we're not going to include infinity, right? Because we cannot contain infinity. So it's a negative infinity to a positive infinity. This is our domain, okay? Another way to write it, they have up here in set notation. X is an element of the set, negative infinity to positive infinity. Another way to say that would be X is an element of all real numbers. Real numbers is indicated with a double-lined R here. That means all real numbers, okay? So these are different ways that you can write the domain for any all exponential functions. All right, so if we should know what the domain is, we should be able to find the range. The range is the next thing. Remember, domain, range, X, Y, input, output. So the range means all the output values, all the Y values. So let's look at this. The set of all possible output values. The range for exponential functions will either be all values above the asymptote or below the asymptote, and the range will never include the asymptote because the curve never actually touches that line. So let's look at these graphs real quick. We see here the dashed line, the green line is the asymptote, and this is exponential growth. It's going up forever and is going out this way forever, right? So the range for this function can never get below this asymptote here, which we know the asymptote is y equals 1, right? This is 1, 2, 3, 4, 5. Y equals 1 is the asymptote. So it will keep approaching and getting closer to y equals 1, but it will never cross it. It will never include it. However, it goes on to infinity in this direction without limit. So that's one type of graph domain you can have for exponential functions. The other is a decay. See, this is decay right here, right? Because it's going down. In this case, the asymptote of y equals 2 is at the top, and the information is going, the graph is going downwards to get away from the asymptote. And then over here, as it approaches y equals 2, it's getting closer and closer and never touches it. So this range cannot be all real numbers because it doesn't go to infinity in both directions. So we need to figure out how to write this with its limiter included. So you could say y is less than whatever k is. In this case, k is 1. So you'd say y is less than 1. You could also say y is greater than, what did I do wrong here? Is y less than k? Well, if k is 1, is y down here? No, it's not. So this one is not y is less than k. I was just looking over here and I wrote that, but I didn't look at my graph. In this case, y is greater than k because all of the y values that's on our curve is above where the asymptote is. So y is greater than k. So y is greater than 1. That's one way to write this. Here's one where y is less than k. Y is less than k. And in this place, because the asymptote is 2, our k is 2. So y is less than 2. Another way to write it, they have up here set notation. Y is an element of the set 1, infinity. Now, that's because you see it has parentheses. It does not include the value of 1 because it never touches that line. It gets really close, but it never touches that line. And remember, we can't contain infinity, so it's got parentheses on both sides. And then another way to write this, it would be an interval notation. Oops, sorry. It's not a bracket, it's a parentheses. It's just going to be like this, okay? This is the range. So y is an element of negative infinity to positive 2. Or we have negative infinity to positive 2. All right, so these are different ways that you can input or write out what your range is. And as you notice, the k is always going to be where the limiter is. The asymptote is the limiter. Okay, so in this case, k was 1. You see the 1, the 1, and the 1. In this case, the asymptote was 2. That's what k is 2. And that's our limiter in each of these ways to write it. All right, so the next thing we want to look at is actually the asymptote. So the asymptote is, remember the line, it's like an imaginary line, it's dashed, you don't graph it necessarily, like you can't see it, we just know that it's there. It's like when we say x has a coefficient of 1, and when I say, oh, it's that implied number 1, I kind of write it dashed like that because we're supposed to know that it's there without me having to tell you. And it's kind of the same way with this asymptote. We dash it in because it's there in theory and an idea, but we don't see it. It's not a part of the graph for us to see to graph. All right, so here we have a graph that's approaching an asymptote. What is the asymptote? The asymptote is y equals 1 because it is the horizontal line that no matter what the x value is, the y value is always 1. Okay, here you have, these are the same asymptotes that we had the last time, same graphs. This is the y equals 2 asymptote. The asymptote is always y equals k. All right, so our next one is the y-intercept. This is where does the graph cross the y-axis. Now, the way they wrote it here, set x equals 0 and solve for y. You're like, what does that even mean? Well, to find the y value of the y-intercept, you will input the set x equal to 0, meaning you're going to substitute 0 in for x and then solve for y. Because remember, our y-intercept is always in the format of x and y, right? It's an ordered pair. And then our x value, when you have a y-intercept, is always going to be 0. And so you have to plug in, if you have an equation, instead of a graph, if you have an equation, you're going to plug the 0 in to substitute for x. Anywhere you see an x, you're going to put in a 0 and then solve for y. And whatever that number is going to go right there. And that's your y-intercept. Now, if you have the graph, it's a little bit easier because you can just look along the y-axis and say, oh, look, it's right there. They made it a huge orange dot. It's right here where the graph, the curve is going to cross the y-intercept. So it's 0, 1, 2, 3. So 0, 3. Oh, look, they have it right there for you. All right, the next thing we need to see is the intervals of increase or the intervals of decrease. Now, all this just means is as x is getting larger, as the function is increased, for the set of all x values for which the function is increasing or decreasing. So the set of x values will either increase everywhere or decrease everywhere. All right, so that doesn't make so much sense in the words. Let's look at the pictures. That'll help us out. The graph is increasing over the entire domain. What's domain? The domain is the x value. So how you read it, it's just like in anything in America, we read left to right. So we're going to read this graph from left to right. And is it increasing or is it decreasing? So remember, it looks like we're going up a mountain. This one is increasing. The values are increasing. So that's what they have here. I don't know if you can read that. And it says from the furthest left to the furthest right, the graph is increasing. So then what's this graph doing? If we go from the left to the right, what's happening? It's going downwards. So it's decreasing. This one is decreasing. Okay, and the value is from infinity, meaning it doesn't ever stop. That's what these mean. I didn't get into it over here. It means it doesn't ever stop. So it's continuously going forever and ever and ever to negative infinity, and it's increasing forever and ever to positive infinity in this direction, right? But it's still decreasing over time because that's the shape of the graph is decreasing. From negative infinity to positive infinity, the graph is decreasing. It's going downwards in a downward fashion in the direction that we read from left to right. All right, end behavior. What's happening at the end of the graph as it leaves our graph paper here, our coordinate plane that we have that we can see, what's happening past what we can see. It's a statement that tells us what the ends of the curve are doing. One end of the curve will either approach positive infinity or negative infinity, and the other end of the curve will approach the asymptote. And this end behavior description is specifically for exponential functions, right? Because this is our first time looking at asymptotes. A function, as it goes to the right, it increases to positive infinity. So how you write that is as x is approaching, as the function goes to the right, it increases to positive infinity. Okay, as x is approaching positive infinity. What does y do? Well, y is also approaching positive infinity. So here, x and y, then we move further towards positive infinity. What's happening to the y? It's increasing as well. It's hard to tell, but it is. As we continue over to increase x, our y is increasing. As we increase x, our y is increasing, right? So as x increases to positive infinity, y is also increasing to positive infinity. And so let's put a little and there, as x is approaching negative infinity, oops, that's a horrible infinity symbol. That means as x is going that way, what is y doing? Well, y is also approaching negative, oh my gracious, infinity. Okay, so as you're moving that direction, both x and y approach negative infinity as well. Okay, so let's look at this one. And I know the answers are down there, but we're going to look at it anyways. As x is approaching positive infinity, what is y approaching? So as x is moving this way, is y going increasing or decreasing? Well, the y values are approaching negative infinity because they're decreasing. So as x is approaching negative infinity, so in other words, as x is going that way, what's happening to the y's? Well, they keep moving up and up and up and up. You can't tell that they're still moving up, but they are. So y is approaching positive infinity. These are the end behaviors. All right, so now this is where we're going to begin to practice this. And if you want to go ahead and press pause and do this one on your own, you can. If you want to go over it first with me and then pause on the next one, that's fine. I do want you to try at least one of these on your own. All right, so You do not have to fill in this chart in the order in which it appears. You do not have to start with the equation. You can start with some of this other information, and that helps us figure out what the equation is. The place where I like to start is the asymptote, because that's the most obvious to me. What is the asymptote? The asymptote is going to be this line right here. It looks like it's approaching this line, and it never ever is going to touch it. It looks like it's touching it, but we know that it's not because it's an asymptote. And that looks to be, let's see, 1, 2, 3, 4, 5. This looks to be y equals 1. All right, what's the y-intercept? That's another easy one. We'll go ahead and do that one. It intercepts the y-axis at 2. So remember, our y-intercept is always an ordered pair with the x being 0, and it intercepts at 2. So that's our y value. Domain, we already know the answer to this. If this is an exponential function, our domain is all real numbers. Or you could say negative infinity to positive infinity. Oops, that should be a parentheses. I don't know why I like to do that first always. Range, well, I know it can't go any lower than 1, and it goes on to positive infinity. So I know it's going to look something like this. My lowest value is 1. My highest value is infinity. And infinity can't be included, so it's going to go like that. And then can it include 1? No, it cannot. So it's going to be a parentheses as well. Is there an interval of increase or an interval of decrease? Well, this looks like if I read my graph from left to right, it is going down. So there is no interval of increase. There is an interval of decrease, and it's from negative infinity to positive infinity. Okay. My end behavior here, my end behavior is going to be what happens. So as x approaches infinity, and then as x approaches negative infinity. Okay, so as x is approaching infinity, what's happening to my y? It's getting less. So y is approaching negative infinity. All right, so going this way, as x approaches negative infinity, my y is getting bigger. So y is approaching positive infinity. Okay, now let's get to writing the equation. I know that this is going to have a +1 at the end because my y equals 1 right here. Okay, well, what if I had this down 1? Let's pretend everything, instead of shifting the line, I'm going to shift the graph paper behind it. So I'm going to say that instead of this being 5, if I shift this graph paper up 1, this 5 is really going to be 4, right? This is 3, this is 2, this is 1, and this is 0. I just shifted everything down, okay? So how that's going to help me is because I'm going to figure out what my base is. Because remember, I have base x minus h a y equals. This is my equation. I already determined what my k was. So I need to see if there's going to be any changes here. Well, if I have a number and I raise it to the power of 0, and it's going to be 1. So base to the power of 0 is 1. Then I know that that means I have not got a multiplier in here of anything. So my multiplier is taken away. I know that this is exponential decay. So I know I'm going to have a fraction. Okay. So let's look at a -1. When it's -1, we're at a +2. So what number raised to the value of -1 is going to equal a +2? Well, how do we solve this? Remember, -1, and we know it's going to be a fraction. And we know the negative means we have to flip it. So this fraction is 2/1. So what do you think our fraction is? 1/2. Well, let's see if that works. 1/2 to the power of -1. Well, the negative means we flip it. So that's 2/1. And this power of 1 gets applied to both 2 and 1. So it looks like I'm correct. So not only do I know that there's no A, now I also know that my B is going to be 1/2. Now I need to see if it moves to the right or left. Well, did I have to change my X value at all? Did my X move to the right or the left? No. When I just applied the -1 that I put in, I got my correct answer. When I plugged in my value of 0, I got the correct answer. So this is just to the power of X. I didn't have to subtract anything from my -1 up here or my 0 or any of that. So my equation is y equals 1/2 X plus 1. All right, I hope you can see that, how we were able to figure out what the equation is. All right, so this time I want you to try it on your own to see if you're able to fill in every one of these. Go ahead and pause the video and come back when you're ready. All right, let's get to it. Asymptote. I see my asymptote is right here, which is y equals what? 1, 2. Okay, so y equals -2 is my asymptote. That means I'm going to have a -2 up there. I already know it, no matter what. My y-intercept is 0, -1. Domain, I already know, is all real numbers. Range is the lowest it can be is going to be -2. And it's going to go on to positive infinity. The interval of increase, yes, this is increasing. So my interval is negative, oh boy, negative infinity to positive infinity. Interval of decrease is none. And behavior, as x is approaching infinity and as x is approaching negative infinity. All right, so as x is approaching infinity, what is y doing? Y is increasing. So y is approaching infinity as well. And as x is approaching negative infinity, what's y doing? Y is decreasing, so negative infinity. Now let's look at what is going on with our graph. I know that this is exponential growth, so I know my b is going to be a whole number, okay? And it's not a reflection, so it's going to be a positive number. I didn't look at that last time, but it is a positive number. It wasn't reflected at all. And let's move the background of this graph. Let's move it down 1. So this is now going to be 0. This is, oops, nope, I want this to be 0. And we'll call this 1, 2, 3, 4, 5, 6, 7, and 8. All right, so when I plug in b to the power of x, if I plug in 0 for my x, I'm going to get 1. Okay, well, that tells me what? What does that tell me? B to the power of 1, that tells me that there's no A. There's no stretch, no vertical stretch or compression going on. So there's no A. That's good to know, no A. And then let's see, there's not going to be an H. So let's just plug some stuff in and see what we get. If we plug in x, the x value of 1 into b to the power of 1 equals, well, what do we get in the graph? 3. B to the power 1 is 3. 0, 1, 2, 3. Okay, well, anything to the power of 1 is going to be what? That's easy enough. 3 to the power of 1 is 3. So what is our b value? Our b value is 3. So our equation is y equals 3 to the power of x minus 2. All right. I hope that you got all of those correct, and we'll see you in the next lesson.